Imagine a place in the universe where a single teaspoon of matter weighs as much as a mountain. Now picture this strange, dense object spinning hundreds of times per second, emitting beams of energy so intense they can be detected across unimaginable distances. Sounds like science fiction, doesn't it? But it's real. These are neutron stars, the universe's most extreme and mysterious cosmic phenomena. Today, we're diving into the depths of space to uncover 50 astonishing facts about the most distant neutron stars ever discovered. These stellar remnants, born from the explosive deaths of massive stars, hold secrets that challenge our understanding of physics, gravity, and the very fabric of the cosmos. From their mind-bending density to their role in creating the gold in your jewelry, neutron stars are not just fascinating, they're essential to the story of the universe itself. So get ready to embark on a journey that will take you to the farthest reaches of space, where incredible discoveries await. By the end of this video, you'll see the universe in a whole new light, and you might just find yourself asking what else is out there that we have yet to uncover. Let's begin. Now, let's start with the basics. What exactly are neutron stars? Picture a colossal star, one that's many times more massive than our Sun, reaching the end of its life. When such a star exhausts its fuel, it doesn't fizzle out quietly. Instead, it goes out with a bang in a spectacular supernova explosion. What's left behind is a neutron star, a stellar corpse so dense it defies imagination. To give you a sense of just how dense, imagine crushing the entire mass of our Sun into a sphere the size of a city. That's a neutron star. Its density is so extreme that a single teaspoon of its material would weigh about as much as Mount Everest. But it's not just their density that makes neutron stars fascinating. They're also the result of one of the most violent events in the universe. The process of their formation compresses matter to the brink of its limits, creating a state of matter that doesn't exist anywhere else. These cosmic powerhouses are not just remnants of stellar explosions, they're laboratories for the most extreme physics, helping us understand the universe in ways no other object can. Now, let's take a closer look at how these incredible neutron stars come into existence. The birth of a neutron star is nothing short of a cosmic spectacle. It begins with the dramatic end of a massive star's life. When a star several times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The star's core collapses inward in a fraction of a second, triggering a cataclysmic supernova explosion that outshines entire galaxies for a brief moment. This explosion blasts the star's outer layers into space, leaving behind a dense, hot core. If the remaining core is between 1.4 and 3 times the mass of the Sun, it doesn't collapse into a black hole. Instead, it becomes a neutron star. This process squeezes protons and electrons together so tightly that they merge to form neutrons, creating an object with unimaginable density. The energy released during this event is staggering enough to outshine 1 billion suns and scatter heavy elements across the cosmos. It's this process that seeds the universe with the building blocks of planets and even life itself. The birth of a neutron star isn't just a violent end, it's a transformative beginning, shaping the universe in ways we're still working to understand. Now let's dive into the astonishing density of neutron stars, a feature that truly sets them apart from anything else in the universe. Picture this: a single sugar cube's worth of material from a neutron star would weigh about as much as Mount Everest. That's right, an object the size of a sugar cube, but with a mass equivalent to the Earth's tallest mountain. This incredible density comes from the way neutron stars are formed. Remember how protons and electrons are squeezed together to form neutrons. That process creates an object so compact that it defies everyday understanding. To put it another way, if you could scoop up a teaspoon of neutron star material, it would weigh billions of tons. This density is a direct result of the star's gravity. which is so strong that it crushes matter into its most compact form. To give you an idea of how extreme this is, imagine compressing the entire human population into the size of a small marble. That's the kind of density we're talking about. It's this mind-bending characteristic that makes neutron stars some of the most fascinating and mysterious objects in the cosmos, challenging our understanding of physics and pushing the boundaries of what we thought was possible. Shifting our focus to another incredible feature of neutron stars, let's talk about their speed of rotation. These cosmic powerhouses can spin hundreds of times per second, making them some of the fastest spinning objects in the universe. To put this into perspective, imagine a figure skater pulling in their arms during a spin, causing them to rotate faster. Neutron stars do something similar. When a massive star collapses into a neutron star, it retains much of its original angular momentum but in a much smaller size. This causes it to spin at astonishing speeds, sometimes completing a full rotation in just a fraction of a second. The fastest known neutron star, called a millisecond pulsar, spins more than 700 times per second. That's faster than the blades of a kitchen blender. This rapid rotation isn't just a curiosity, it's a key feature that helps astronomers detect and study these objects. As they spin, they emit beams of radiation that can be observed from Earth, acting like cosmic lighthouses. This incredible speed also has implications for the star's structure and the extreme forces at play on its surface. It's yet another example of how neutron stars push the boundaries of what we thought was possible in the universe, challenging our understanding of physics and leaving us in awe of their sheer power and mystery. Now, let's turn our attention to pulsars, a fascinating type of neutron star that acts as a beacon in the cosmos. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As these stars spin at incredible speeds, their beams sweep across space, much like the light from a lighthouse rotates to guide ships. When one of these beams points toward Earth, we can detect it as a rapid, rhythmic pulse of radiation. This is why they're called pulsars, short for pulsating stars. These pulses are so regular that some pulsars rival atomic clocks in their precision. The first pulsar was discovered in 1967 by astronomers Jocelyn Bell Burnell and Anthony Hewish, who initially dubbed the signal "little green men" due to its rhythmic nature. But what causes these beams? It's a result of the neutron star's intense magnetic field, which accelerates charged particles, causing them to emit radiation along the magnetic poles. This process creates the bright beams that we observe. Pulsars aren't just cosmic oddities, they're incredibly useful tools for astronomers. By studying their pulses, scientists can learn about the structure of neutron stars, measure distances in space, and even test theories of gravity. These cosmic lighthouses continue to illuminate the mysteries of the universe, offering us a glimpse into the extraordinary physics at play in some of the most extreme environments imaginable. Now, shifting our focus to a more extreme cousin of pulsars, let's dive into the world of magnetars. These neutron stars are not just dense and fast spinning, they possess magnetic fields so powerful they defy imagination. To put it into perspective, a magnetar's magnetic field can be a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. This immense magnetic energy makes magnetars some of the most destructive and fascinating objects in the universe. These stars are capable of producing starquakes, which are similar to earthquakes but on a cosmic scale. During a starquake, the magnetar's crust cracks and shifts, releasing enormous amounts of energy in the form of gamma-ray bursts. These bursts are among the most energetic events in the cosmos, capable of outshining entire galaxies for a brief moment. Even more astonishing is that a single gamma-ray burst from a magnetar can release more energy in a fraction of a second than our Sun will emit in its entire 10 billion-year lifespan. Despite their destructive power, magnetars are also invaluable to scientists. Studying them helps us understand the limits of magnetic fields, the behavior of matter under extreme conditions, and the nature of these cosmic powerhouses. Magnetars remind us that the universe is full of forces far beyond our everyday experience, yet they hold the keys to unlocking some of its deepest mysteries. Now, let's venture even further into the cosmos to explore the most distant neutron stars. These celestial objects are located billions of light years away, making them some of the most remote and enigmatic structures in the universe. Detecting them is no small feat. Scientists rely on advanced telescopes that can capture X-rays, gamma rays, and radio waves, as these are the signals neutron stars emit most strongly. However, the vast distances make these signals incredibly faint by the time they reach Earth. It's like trying to spot a single firefly's glow from thousands of miles away. Adding to the challenge is the fact that neutron stars are often nestled within dense regions of space, such as supernova remnants or near other massive objects, which can obscure their signals even further. Despite these hurdles, studying the most distant neutron stars is crucial. They act as cosmic time capsules, preserving information about the early universe and the conditions that existed billions of years ago. By analyzing their light and signals, scientists can piece together the history of star formation, galaxy evolution, and even the expansion of the universe itself. These distant neutron stars remind us that the universe is not just vast but also filled with clues waiting to be uncovered, even from the farthest reaches of space. Moving forward, let's dive into one of the most groundbreaking discoveries in modern astronomy: the connection between neutron stars and gravitational waves. When neutron stars collide, they create ripples in the fabric of space-time, known as gravitational waves. These waves travel across the universe at the speed of light, carrying information about the violent events that produce them. The first detection of gravitational waves from a neutron star collision in 2017 marked a monumental moment in science, confirming predictions made by Albert Einstein over a century ago. These collisions not only produce gravitational waves but also unleash incredible bursts of energy, including gamma-ray bursts and the creation of heavy elements like gold and platinum. By studying these waves, scientists can learn more about the properties of neutron stars, such as their mass, size, and internal structure. Gravitational waves also provide a new way to observe the universe, allowing researchers to listen to cosmic events that would otherwise remain hidden. This breakthrough has opened up a whole new field of astronomy, offering insights into the most extreme environments in the cosmos. As we continue to detect and analyze these waves, neutron stars will remain at the forefront of our quest to understand the universe's deepest mysteries. Now, let's shift our focus to something truly extraordinary: the sound of neutron stars. While we can't physically hear these distant cosmic objects, scientists have found a way to translate the gravitational waves produced by neutron star collisions into sound. This process, known as sonification, takes the ripples in space-time and converts them into audible frequencies. Imagine listening to the echoes of two neutron stars colliding billions of light years away. These sounds provide a unique way for researchers to study these events, offering an auditory glimpse into the most violent and energetic processes in the universe. The result is a series of chirps, tones, or waves that vary depending on the nature of the collision. By analyzing these sounds, scientists can gather insights into the mass, spin, and distance of the neutron stars involved. This innovative approach not only enriches our understanding of these cosmic phenomena, but also brings the universe to life in a way that's both captivating and accessible. It's a reminder that sometimes the most profound discoveries come from finding new ways to experience the cosmos. Now, let's dive into one of the most spectacular events in the cosmos: neutron star collisions. These encounters are not only rare but also incredibly violent, releasing more energy in a few seconds than our Sun will emit over its entire lifetime. When two neutron stars collide, their immense gravitational forces cause them to spiral toward each other, eventually merging in a cataclysmic explosion. This collision sends ripples through space-time, known as gravitational waves, and produces a burst of light across multiple wavelengths, from gamma rays to radio waves. But the most fascinating outcome of these collisions is the creation of heavy elements. During the merger, the extreme conditions generate nuclear reactions that forge elements like gold, platinum, and uranium. These newly formed elements are then scattered into space, seeding the universe with the building blocks of planets and even life. In fact, much of the gold and platinum found on Earth may have originated from neutron star collisions billions of years ago. These events not only shape the cosmos but also remind us of our connection to the stars, as the very atoms that make up our world were born in these distant, fiery encounters. Moving beyond their explosive collisions, neutron stars play a much broader role in shaping the universe. These dense remnants of stellar explosions are not just cosmic curiosities, they are active participants in the evolution of galaxies. One of their most significant contributions is the production of heavy elements. Through processes like neutron star mergers, these objects create and disperse elements such as gold, platinum, and uranium into the cosmos. These elements eventually become part of new stars, planets, and even the building blocks of life itself. But neutron stars don't stop there. Their intense gravitational and magnetic fields can influence the space around them, often triggering the formation of new stars by compressing nearby gas clouds. Additionally, their powerful beams of radiation can strip atmospheres from neighboring planets or alter the chemical makeup of surrounding regions in space. Neutron stars also act as cosmic laboratories, helping scientists test theories about gravity, matter, and the fundamental laws of physics. By studying these distant objects, we gain insights into the universe's past, present, and future. From seeding the cosmos with essential elements to shaping the dynamics of their local environments, neutron stars are truly architects of the universe's ongoing story. Now, let's take a closer look at the sheer compactness of neutron stars. Despite their incredible mass, these cosmic marvels are astonishingly small. To put it into perspective, a typical neutron star measures about 20 kilometers in diameter. That's roughly the size of a small city on Earth. Yet within this tiny space, a neutron star holds a mass 1.4 times that of our Sun. Imagine squeezing Mount Everest into a sugar cube. That's the kind of density we're talking about. To give you an even clearer idea, if you could take a teaspoon of neutron star material, it would weigh about as much as 300 billion cars. That's enough to cover the entire surface of the Earth multiple times over. What makes this even more mind-blowing is the fact that neutron stars are only slightly larger than black holes, but they manage to hold themselves together without collapsing completely. Their immense density and compact size make them some of the most extreme objects in the universe, defying our everyday understanding of physics. This incredible balance of mass and size is a testament to the universe's ability to create objects that push the boundaries of what we thought was possible. Now, let's step into the realm of Einstein's theory of relativity with a fascinating effect tied to neutron stars: time dilation. These incredibly dense objects possess gravitational fields so intense that they actually warp time itself. Near the surface of a neutron star, time slows down compared to how it passes in regions with weaker gravity, like here on Earth. To give you an idea of how extreme this effect is, imagine a clock placed on the surface of a neutron star. For every second that ticks by on that clock, multiple seconds would pass for an observer far away in space. This happens because the immense gravitational pull of the neutron star bends space-time, creating a sort of time trap. Scientists use this phenomenon to test and confirm predictions made by Einstein's theory of general relativity. Time dilation isn't just a theoretical curiosity. It's a real, measurable effect that demonstrates how gravity and time are deeply intertwined. Next up, we'll see how neutron stars compare to their mysterious counterparts, black holes. Now, let's turn our attention to how neutron stars stack up against one of the universe's most enigmatic objects, black holes. Both neutron stars and black holes are born from the dramatic deaths of massive stars, but they represent two very different paths in the cosmic life cycle. When a star exhausts its nuclear fuel, it collapses under its own gravity. If the remnant core is between about 1.4 and 3 times the mass of our Sun, it becomes a neutron star. But if the core is more massive than that, it continues collapsing into a black hole where gravity becomes so strong that not even light can escape. Interestingly, neutron stars and black holes share some similarities. Both are incredibly dense, and their gravitational fields are so intense that they warp the fabric of spacetime. However, while neutron stars have a solid surface, black holes have an event horizon, a point of no return where the pull of gravity becomes unstoppable. Another key difference lies in their visibility. Neutron stars, especially pulsars, emit beams of radiation that we can detect, while black holes are invisible unless they're actively consuming matter, creating bright accretion disks. These two cosmic extremes not only showcase the incredible diversity of the universe, but also help us understand the limits of physics and the fate of stars. Coming up next, we'll explore the tools and techniques astronomers use to search for these elusive neutron stars. Now, let's shift our focus to the fascinating methods astronomers use to hunt for these elusive neutron stars. One of the most effective tools in this search is the radio telescope. These powerful instruments detect the radio waves emitted by pulsars, a type of neutron star that beams radiation like a cosmic lighthouse. By capturing these signals, astronomers can pinpoint the location and behavior of pulsars across vast distances. Another crucial tool is the X-ray observatory. Neutron stars, especially those in binary systems or magnetars, emit intense X-rays. Satellites like the Chandra X-ray Observatory are designed to detect these high-energy emissions, providing a unique window into the extreme environment surrounding neutron stars. Additionally, gravitational wave detectors such as LIGO and Virgo play a vital role. When neutron stars collide or merge with other compact objects, they send ripples through spacetime that these detectors can pick up. This not only helps locate neutron stars but also offers insights into their properties and the dynamics of such violent events. Together, these methods, radio telescopes, X-ray observatories, and gravitational wave detectors, form a comprehensive toolkit that allows scientists to uncover the secrets of neutron stars hidden in the farthest corners of the universe. Next, we'll delve into the astonishing age of some neutron stars and what they can tell us about the early cosmos. Turning our attention to the ancient relics of the cosmos, some neutron stars are astonishingly old, with ages stretching back billions of years. These cosmic time capsules offer a unique glimpse into the early universe, preserving clues about the conditions and events that shaped its infancy. Imagine, for a moment, a neutron star that formed shortly after the Big Bang, still spinning and emitting radiation today. These ancient objects serve as natural laboratories, helping scientists piece together the story of how stars and galaxies first emerged. By studying their properties, such as their rotation rates and magnetic fields, astronomers can infer the environment in which they were born. For instance, slower spinning neutron stars are often older, as their rotation gradually slows over time. Additionally, the composition of their surfaces and the way they interact with surrounding matter can reveal details about the chemical makeup of the early universe. These ancient neutron stars are not just remnants of the past, they are keys to unlocking the mysteries of how our universe evolved from its fiery beginnings to the complex cosmos we see today. Next, we'll explore the fascinating connection between neutron stars and the remnants of supernova explosions, shedding light on their dramatic origins. Now let's delve into the dramatic aftermath of supernova explosions and their intimate connection to neutron stars. When a massive star reaches the end of its life, it doesn't simply fade away, it explodes in a cataclysmic event known as a supernova. This explosion leaves behind two remarkable cosmic signatures, a neutron star and a supernova remnant. These remnants are vast, glowing clouds of gas and dust expanding outward into space at incredible speeds. Interestingly, neutron stars are often found at the heart of these remnants, acting as the dense, spinning cores left behind after the explosion. The interaction between neutron stars and their surrounding remnants is a dynamic process. As the neutron star spins, it emits radiation and particles that can energize the surrounding gas, creating intricate structures and shock waves within the remnant. By studying these interactions, astronomers can learn more about the conditions during the supernova explosion and the life cycle of stars. Supernova remnants also serve as cosmic recycling centers, dispersing heavy elements forged in the star's core and the explosion itself back into the universe. This material eventually becomes part of new stars, planets, and even life. The connection between neutron stars and supernova remnants not only highlights the violent beauty of stellar death, but also underscores their role in the ongoing cycle of cosmic creation. Next, we'll uncover how neutron stars often find themselves in binary systems, creating even more fascinating astronomical phenomena. Now, shifting our focus to the cosmic dance of neutron stars, let's explore their fascinating existence in binary systems. Neutron stars don't always roam the universe alone. They often find themselves paired with another star, locked in a gravitational embrace. These binary systems are like celestial laboratories, offering scientists a front-row seat to some of the most extreme and intriguing phenomena in space. When a neutron star orbits a companion star, it can pull material from its partner, creating a swirling disk of gas and dust around the neutron star. This process, known as accretion, releases immense amounts of energy, often detected as X-rays or even gamma rays. In some cases, the interaction between the neutron star and its companion can lead to spectacular bursts of energy called X-ray bursts, lighting up the cosmos in dazzling flashes. Binary systems also provide an opportunity to study the effects of intense gravitational fields. As the neutron star and its companion orbit each other, they can emit gravitational waves, ripples in space-time that reveal valuable information about their masses and distances. These systems have even helped scientists confirm predictions made by Einstein's theory of general relativity. One of the most famous examples of a neutron star binary system is the Hulse-Taylor binary, discovered in the 1970s. This system consists of a neutron star and a pulsar orbiting each other, and its discovery provided the first indirect evidence of gravitational waves, earning its discoverers the Nobel Prize in Physics. Neutron stars in binary systems continue to captivate astronomers, offering insights into the fundamental laws of physics and the dynamic processes that shape our universe. Next, we'll take a closer look at the surface of neutron stars and the extreme conditions that define their existence. Now, let's step onto the surface of a neutron star, a place so extreme it defies imagination. The surface of a neutron star is unlike anything we could ever experience on Earth. For starters, it's incredibly smooth despite their rugged appearance in illustrations. Neutron stars have surfaces that are thought to be so perfectly even that any mountains would only be a few millimeters high. This is due to the immense gravitational pull which crushes any irregularities into near flatness. Temperatures here are equally mind-blowing. Right after a neutron star forms, its surface can reach up to 1 million degrees Celsius, hot enough to vaporize any known material. Over time, it cools, but even then, it remains scorching by Earth standards, often hovering around hundreds of thousands of degrees. The pressure on the surface is equally staggering. Because neutron stars pack the mass of our Sun into a sphere roughly the size of a city, the pressure at the surface is trillions of times greater than what we experience on Earth. This combination of extreme heat and pressure creates conditions where atoms can't exist as we know them. Instead, the surface is thought to be a solid crust made of atomic nuclei arranged in a crystalline lattice, with electrons and neutrons packed tightly together. Beneath this crust, the material becomes even denser, transitioning into a superfluid of neutrons. These extreme conditions make the surface of a neutron star a unique and hostile environment, offering scientists a glimpse into matter under conditions that can't be replicated anywhere else in the universe. Next, we'll explore how neutron stars contribute to the acceleration of cosmic rays, high-energy particles that travel through space. Now, let's shift our focus to a phenomenon that connects neutron stars to the vast expanse of space around them: cosmic rays. These high-energy particles, traveling at nearly the speed of light, are one of the universe's greatest mysteries. Neutron stars, with their extreme environments, are thought to play a significant role in accelerating these particles to such incredible speeds. The intense magnetic fields of neutron stars, especially in pulsars and magnetars, act as natural particle accelerators. Charged particles like protons and electrons get caught in these magnetic fields and are whipped around at tremendous velocities. Over time, they gain enough energy to break free, shooting out into space as cosmic rays. These particles, once released, can travel billions of light years, carrying with them information about the extreme conditions that created them. What's even more fascinating is that neutron stars aren't just random accelerators. Their precise rotations and focused magnetic fields allow them to channel these particles in specific directions, sometimes creating jets of cosmic rays that can be detected across the universe. This process not only helps scientists study the properties of neutron stars, but also provides clues about the origins of cosmic rays themselves. By understanding how neutron stars contribute to this phenomenon, we gain deeper insight into the forces that shape our universe. Up next, we'll delve into what happens to neutron stars as they age, exploring their lifespan and evolution over billions of years. Neutron stars, born from the fiery remnants of supernova, embark on a journey that spans billions of years, gradually cooling and evolving as they age. Over time, these incredibly dense objects lose their heat, radiating energy into the surrounding space. Initially, a neutron star's surface temperature can reach millions of degrees, but as it ages, this temperature drops significantly. The cooling process is influenced by factors like its composition, magnetic field strength, and interactions with surrounding matter. As neutron stars cool, their internal structure changes too. The intense pressure within them causes the neutrons to behave in unique ways, sometimes forming exotic states of matter like superfluids which flow without friction. Over billions of years, neutron stars may become quieter and dimmer, emitting less radiation overall. However, even as they age, their immense gravitational pull and magnetic fields continue to influence their surroundings. Some neutron stars may eventually fade into obscurity, while others might encounter nearby matter, reigniting bursts of energy. This gradual cooling and transformation not only reveal the life cycle of these cosmic giants, but also provide clues about the universe's history. Next, we'll explore how neutron stars challenge our understanding of the speed of light and the fundamental laws of physics. Now, let's shift our focus to how neutron stars push the boundaries of our understanding of the speed of light and the very fabric of space and time. These cosmic powerhouses, with their extreme gravitational fields and rapid rotations, create conditions that challenge the fundamental principles of physics. One of the most intriguing aspects of neutron stars is their ability to bend light due to their immense gravity. In fact, light itself struggles to escape their pull, making them natural laboratories for testing Einstein's theory of relativity. Scientists study how light behaves near neutron stars to confirm predictions about time dilation, where time passes more slowly in stronger gravitational fields. This effect has been observed in pulsars, where the intense gravity causes their signals to slow down as measured from Earth. Additionally, the rapid spin of neutron stars, sometimes hundreds of times per second, creates conditions that could help scientists explore the limits of the speed of light. Some theories suggest that the extreme environment of neutron stars might reveal new insights into how light and gravity interact on a cosmic scale. By observing these distant stellar remnants, researchers gain a deeper understanding of the universe's most fundamental laws, shedding light on the mysteries of space, time, and the speed of light. Next, we'll delve into the fascinating discovery of the first neutron star and its groundbreaking impact on astronomy. Moving from the theoretical to the historical, let's turn our attention to the moment when the first neutron star was discovered, a breakthrough that forever changed our understanding of the cosmos. In 1967, a young astronomer named Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed something extraordinary. She detected a series of rapid, rhythmic pulses coming from deep space, repeating every 1.337 seconds. At first, these signals were so precise that they were jokingly nicknamed "little green men," as some speculated they could be messages from an extraterrestrial civilization. However, further research revealed the true source, a rapidly rotating neutron star now known as a pulsar. This discovery was monumental, not only because it confirmed the existence of neutron stars, but also because it provided a new tool for exploring the universe. Pulsars, with their predictable signals, became cosmic lighthouses, allowing scientists to measure distances in space and study the properties of matter under extreme conditions. Jocelyn Bell Burnell's work earned her a place in the history of astronomy, though her contributions were initially overshadowed by her male colleagues. Today, her discovery is celebrated as a pivotal moment in astrophysics, opening the door to countless insights into the nature of neutron stars and the mysteries of the universe. Next, we'll explore how neutron stars might hold clues to one of the universe's greatest enigmas, dark matter. Now, stepping into the realm of the unknown, let's delve into how neutron stars might hold the key to unlocking one of the universe's biggest mysteries, dark matter. Neutron stars, with their immense gravitational fields and dense cores, could serve as cosmic laboratories for studying this elusive substance. Scientists theorize that dark matter particles, which make up about 27% of the universe, might interact with neutron stars in subtle but detectable ways. For example, dark matter could accumulate in the core of a neutron star over time, altering its properties and potentially slowing its rotation. These interactions could provide indirect evidence of dark matter's existence and help us understand its nature. Some researchers even suggest that neutron stars could act as traps for dark matter, capturing particles and enabling us to study their effects. By observing neutron stars, astronomers hope to gather clues about how dark matter influences the universe on both large and small scales. This connection between neutron stars and dark matter not only deepens our understanding of these enigmatic objects, but also brings us closer to solving one of the most profound questions in modern physics. Next, we'll explore how neutron stars play a role in shaping the very fabric of our galaxy. Shifting our gaze to the grand scale of the cosmos, let's consider the remarkable role neutron stars play in shaping the evolution of galaxies. These dense remnants of supernova explosions are not just isolated wonders. They actively influence the structure and movement of stars and gas within galaxies. When a neutron star forms, the energy released during the supernova can trigger waves of star formation by compressing nearby gas clouds. Over billions of years, neutron stars contribute to the dynamic environment of galaxies, sometimes interacting with other stars or even black holes in ways that alter their paths. Additionally, neutron stars often travel at high speeds, ejected from their birthplaces by the force of the supernova explosion. As they move through the galaxy, they can disrupt the orbits of other objects, adding to the complex dance of cosmic evolution. Their powerful magnetic fields and emissions of radiation also influence the surrounding space, heating up gas and affecting how stars form. By studying neutron stars, astronomers gain insights into the processes that drive galactic change, helping us understand how galaxies, including our own Milky Way, have grown and transformed over time. This connection between neutron stars and galactic evolution highlights their importance not just as individual objects, but as key players in the larger story of the universe. Next, we'll explore how neutron stars might even hold clues to the search for life beyond our planet. Now, let's turn our attention to a fascinating question. Could neutron stars hold the key to finding life beyond Earth? While neutron stars are known for their extreme conditions, intense gravity, scorching temperatures, and powerful magnetic fields, they might still play a role in the search for alien life. One intriguing possibility lies in their potential to host planets. Despite their harsh environments, some neutron stars could have planets orbiting them, known as pulsar planets. These planets, though rare, might survive in stable orbits, shielded from the star's radiation by their distance. While the surface conditions would likely be inhospitable, life could, in theory, exist in subsurface oceans or other protected environments. Additionally, neutron stars could provide indirect clues about life elsewhere in the universe. For example, the heavy elements created in neutron star collisions, like gold and platinum, are essential building blocks for planets and life as we know it. By studying these elements, scientists can trace the cosmic origins of the materials that make life possible. Neutron stars might also serve as natural laboratories, helping us understand the limits of life in extreme conditions and guiding our search for habitable worlds. While the idea of life around neutron stars remains speculative, it opens up exciting possibilities for future discoveries. Next, we'll dive into the rhythmic signals of pulsars, often described as the cosmic lighthouses of the universe. Now, let's tune into the cosmic symphony of pulsars, where the universe itself seems to keep a rhythmic beat. Pulsars, a type of neutron star, emit beams of radiation that sweep across space like the light from a lighthouse. What makes them truly unique is the regularity of these pulses. As the pulsar spins, its beams of radiation are detected on Earth as precise, repeating signals. Astronomers have found ways to translate these signals into sounds, transforming the cosmic rhythm into something we can hear. Imagine a steady ticking or a musical beat, each pulse representing a rotation of the pulsar. Some even produce tones that resemble musical notes, creating a kind of celestial melody. These rhythmic signals are so consistent that they rival the precision of atomic clocks, making pulsars some of the most accurate timekeepers in the universe. The study of these sounds not only helps scientists understand the behavior of pulsars, but also provides a unique way to explore the cosmos. Next, we'll explore how neutron stars can be used to measure the expansion of the universe itself. Moving deeper into the mysteries of the cosmos, neutron stars also play a surprising role in helping us understand the expansion of the universe. These dense stellar remnants are not just fascinating objects in their own right, they are also powerful tools for astronomers. By observing neutron stars, particularly pulsars, scientists can measure the rate at which the universe is expanding. How do they do this? Pulsars emit incredibly regular signals, so precise that they can be used to track tiny changes in the distances between these stars and Earth. When combined with other cosmic measurements, such as those from distant supernova or the cosmic microwave background, neutron stars help refine calculations of the Hubble constant, the rate of the universe's expansion. This is crucial for testing cosmological theories, including those about dark energy, the mysterious force driving this acceleration. Neutron stars, in a sense, act as cosmic yardsticks, stretching our understanding of the universe's growth on the grandest scale. Next, we'll uncover the discovery of the most massive neutron stars and how they challenge our understanding of physics itself. Now, let's turn our attention to one of the most jaw-dropping discoveries in the realm of neutron stars, their sheer mass. The most massive neutron stars ever discovered push the boundaries of what we thought was physically possible. These cosmic heavyweights, often weighing in at around 2.1 times the mass of our Sun, are so dense that they teeter on the edge of collapsing into black holes. What makes them truly remarkable is how they challenge our understanding of the fundamental laws of physics. For instance, their extreme density forces us to reconsider the behavior of matter under such unimaginable pressure. Inside these stars, matter is compressed to a state where protons and electrons merge to form neutrons, creating an environment that defies our everyday experiences. Scientists use observations of these massive neutron stars to test theories about the strong nuclear force, the force that holds atomic nuclei together. If these stars were just a bit more massive, they would collapse into black holes, making them a crucial boundary between two of the universe's most extreme objects. Their existence not only deepens our understanding of neutron stars, but also provides a unique testing ground for the laws of physics themselves. Next, we'll dive into how neutron star collisions create elements like gold, platinum, and uranium, enriching the universe with the building blocks of life. Now, let's explore one of the most fascinating roles neutron stars play in the cosmos, the creation of heavy elements. When two neutron stars collide, the sheer power of this cosmic event is enough to forge some of the universe's most precious materials. Elements like gold, platinum, and uranium, which are essential to life as we know it, are born in the fiery aftermath of these collisions. During such an event, the intense energy and pressure cause neutrons to bombard atomic nuclei, creating heavier elements in a process known as rapid neutron capture, or the R process. This process doesn't just produce a few atoms, it generates vast quantities of these elements, which are then scattered across space. These materials eventually become part of new stars, planets, and even life itself. It's incredible to think that the gold in your jewelry or the uranium used in nuclear reactors likely originated from a neutron star collision billions of years ago. These cosmic encounters not only enrich the universe but also remind us of the interconnectedness of all things. Next, we'll uncover how neutron stars contribute to some of the most energetic events in the cosmos, gamma-ray bursts. Shifting our focus to the sheer power of neutron stars, let's uncover their connection to gamma-ray bursts, some of the most explosive events in the universe. These bursts are incredibly bright flashes of gamma rays, the most energetic form of light, and they can outshine entire galaxies for a brief moment. Neutron stars play a key role in producing these bursts, especially when they collide with another neutron star or a black hole. The collision releases an enormous amount of energy, creating jets of particles that travel at nearly the speed of light. These jets emit gamma rays as they interact with surrounding space, resulting in the bursts we detect. But that's not all. Some gamma-ray bursts are linked to magnetars, neutron stars with ultra-strong magnetic fields. When a magnetar experiences a starquake, a sudden shift in its crust, it releases a massive amount of energy, triggering a burst. These events are so powerful that they can be observed billions of light years away, offering scientists a window into the most extreme conditions in the universe. Next, we'll delve into how neutron stars might even hold clues to the mysterious concept of a multiverse. Now, let's take a step into one of the most intriguing and speculative areas of science: the possibility that neutron stars could be connected to the concept of a multiverse. While the idea of multiple universes existing alongside our own might sound like science fiction, some theories in physics suggest it could be a reality. Neutron stars, with their extreme densities and gravitational fields, might offer clues to this mind-bending idea. One theory proposes that the intense conditions near neutron stars could create ripples in space-time, potentially revealing hidden dimensions or pathways to other universes. These ripples, if detected, could provide evidence for the existence of a multiverse. Another fascinating idea is that neutron-star collisions, which release enormous amounts of energy, might create temporary bridges or wormholes connecting different universes. While these theories are still speculative and require much more research, they highlight how neutron stars could be at the forefront of answering some of the biggest questions in physics. What's next? We'll explore how studying neutron stars could lead to the discovery of entirely new physical laws. Shifting our focus to the cutting edge of physics, neutron stars serve as extraordinary cosmic laboratories for uncovering new physical laws. These ultra-dense remnants of stellar explosions push the boundaries of our understanding, offering insights into phenomena that cannot be replicated on Earth. For instance, the extreme gravitational forces on neutron stars allow scientists to test predictions of Einstein's theory of general relativity under conditions far more intense than those found on our planet. Additionally, the behavior of matter under such immense pressure challenges our current models of quantum mechanics, potentially revealing gaps or new principles in physics. Observations of neutron star collisions, which produce gravitational waves and heavy elements, also provide valuable data that could lead to fresh discoveries. Some researchers even speculate that studying neutron stars might help uncover a unified theory of physics, bridging the gap between the laws governing the very large and the very small. As we continue to probe these celestial objects, the possibilities for uncovering groundbreaking physics are as vast as the universe itself. Next, we'll dive into how neutron stars might interact with supermassive black holes at the hearts of galaxies. Now, let's venture into the heart of galaxies, where neutron stars and supermassive black holes engage in a cosmic dance that shapes the fabric of the universe. At the center of nearly every galaxy, including our Milky Way, lies a supermassive black hole, a gravitational giant millions or even billions of times more massive than our Sun. Surrounding these black holes are dense clusters of stars, including neutron stars, which often find themselves in a perilous orbit around these gravitational behemoths. When a neutron star gets too close to a supermassive black hole, the black hole's immense gravitational pull can stretch and distort the neutron star in a process known as spaghettification. This violent interaction can result in dramatic events, such as bursts of radiation or even the complete destruction of the neutron star. In some cases, neutron stars that survive their close encounter with a black hole can emit powerful gravitational waves, ripples in space-time that provide scientists with valuable insights into the behavior of these extreme objects. These interactions also play a crucial role in shaping the dynamics of galactic centers, influencing the movement of stars and gas clouds. By studying these encounters, astronomers can better understand the complex processes that govern the evolution of galaxies. Next, we'll explore how neutron stars might influence the ultimate fate of the universe itself. Shifting our gaze to the grandest scale, let's consider how neutron stars might shape the ultimate destiny of the universe itself. One of the most debated theories about the universe's fate is the concept of heat death, where all energy is evenly distributed, and stars, galaxies, and other cosmic structures fade into eternal darkness. Neutron stars, with their immense density and slow cooling over billions of years, play a part in this process. As they radiate away their energy, they contribute to the gradual cooling of the universe, inching closer to this state of universal equilibrium. On the other hand, some theories suggest the universe could end in a big crunch, where gravitational forces pull everything back into a singular point. In this scenario, neutron stars, along with black holes and other dense objects, could accelerate the collapse, their immense gravity pulling matter inward. Even in their seemingly silent existence, neutron stars act as cosmic timekeepers, their evolution offering clues about the universe's timeline. Whether the universe ends in heat death or a big crunch, neutron stars remain key players in this cosmic drama, their behavior helping scientists piece together the ultimate story of existence. Next, we'll delve into how neutron stars can trigger the birth of new stars, continuing their influence on the cosmic cycle. Turning our attention to the life-giving potential of neutron stars, let's explore their surprising role in star formation. While these dense remnants are often associated with destruction, they can also act as cosmic catalysts for creation. When a neutron star passes through or near a cloud of interstellar gas, its immense gravitational pull compresses the gas, increasing its density. This compression can trigger the collapse of the gas cloud, a crucial first step in the birth of new stars. Think of it like squeezing a sponge. Apply enough pressure, and eventually something spectacular happens. In this case, the pressure from the neutron star's gravity ignites the process of star formation, transforming cold, diffuse gas into the seeds of future stars. This phenomenon highlights the dual nature of neutron stars. They can end one stellar life while giving rise to another. By studying these interactions, scientists gain deeper insights into the cycle of stellar life and death, showing that even in the vastness of space, destruction and creation are often intertwined. Next, we'll venture into the realm of speculative physics, where neutron stars might hold the key to uncovering wormholes in the fabric of space-time. Taking a leap into the realm of speculative physics, let's explore how neutron stars could be linked to one of the most fascinating concepts in science: wormholes. Wormholes, often referred to as Einstein-Rosen bridges, are hypothetical tunnels through space-time that could connect distant parts of the universe or even different universes altogether. While they've been a staple of science fiction, scientists have theorized that neutron stars might hold the key to making wormholes a reality. The extreme gravitational fields and immense density of neutron stars could create the right conditions for these space-time tunnels to form. Some theories suggest that the intense pressures and magnetic fields near neutron stars might stabilize a wormhole, preventing it from collapsing instantly. While this remains speculative, the idea that neutron stars could act as gateways to other regions of space is both thrilling and mind-bending. By studying these cosmic objects, we might one day uncover clues about the true nature of space-time and whether wormholes are more than just a theoretical construct. As we continue to probe the mysteries of neutron stars, we inch closer to answering some of the universe's most profound questions. Next, we'll dive into how neutron stars can produce some of the most powerful jets in the cosmos. Shifting our focus to another extraordinary phenomenon, neutron stars are not just dense cosmic wonders, they're also capable of launching some of the most powerful jets in the universe. These astrophysical jets are narrow streams of particles that shoot out at nearly the speed of light, often extending for thousands of light years across space. So, how do neutron stars produce such incredible jets? It all comes down to their intense magnetic fields and rapid rotation. As matter spirals toward a neutron star, it gets funneled along the magnetic field lines, accelerating to extreme speeds. Some of this material is then ejected perpendicular to the star's magnetic poles, forming those spectacular jets. What's even more fascinating is that these jets can carry enough energy to outshine entire galaxies, even though they're emanating from an object just a few miles across. Neutron stars aren't the only celestial objects that produce jets. Black holes do too, but neutron star jets are unique because they're often accompanied by bursts of X-rays and gamma rays, providing scientists with valuable clues about the physics at play. These jets also play a crucial role in shaping their surrounding environments, influencing star formation and even the evolution of galaxies. As we continue to study these cosmic powerhouses, we uncover more about how neutron stars contribute to the dynamic and ever-changing universe around us. Next, we'll examine how neutron stars might have played a role in the origin of life itself. Now, let's explore one of the most intriguing possibilities. Could neutron stars have played a role in the origin of life? While it might sound like science fiction, there's a compelling theory that links these distant cosmic objects to the building blocks of life. When neutron stars collide, they unleash immense energy and create heavy elements like gold, platinum, and uranium. But they also produce lighter elements such as carbon, nitrogen, and oxygen, which are essential for life as we know it. These elements are scattered into space by the force of the collision, eventually becoming part of interstellar clouds. Over time, these clouds can collapse to form new stars and planets, seeding them with the necessary ingredients for life. Some scientists even suggest that the intense radiation and shock waves from neutron star collisions could have triggered chemical reactions in these clouds, accelerating the formation of complex molecules. While we're still piecing together the full story, it's fascinating to think that the remnants of a neutron star's explosive death might have indirectly contributed to the rise of life on Earth and possibly elsewhere in the universe. As we continue our journey through the mysteries of neutron stars, let's turn our attention to how they might leave their mark on the cosmic microwave background radiation. Shifting our focus to another cosmic connection, let's delve into how neutron stars might interact with the cosmic microwave background radiation, or CMB for short. The CMB is often described as the afterglow of the Big Bang, a faint energy signature that permeates the entire universe. But what does this have to do with neutron stars? While neutron stars themselves don't directly emit CMB, their presence and activity can subtly influence its properties. For instance, when neutron stars collide or emit powerful bursts of energy, these events can create ripples in the fabric of space-time known as gravitational waves. These waves can interact with the CMB, leaving faint but detectable imprints. Additionally, the intense magnetic fields and radiation from neutron stars might contribute to tiny fluctuations in the CMB's uniformity. Scientists are actively studying these potential effects, as they could provide new insights into both neutron stars and the early universe. By analyzing these imprints, researchers hope to uncover hidden details about the formation and evolution of these enigmatic objects. This interplay between neutron stars and the CMB adds yet another layer to our understanding of the cosmos, showing how even the most distant objects can leave their mark on the universe's oldest light. Let's now explore how neutron stars could provide clues about the existence of extra dimensions. Neutron stars might just hold the key to unlocking one of the universe's most profound mysteries, the existence of extra dimensions. While we live in a world defined by three spatial dimensions: length, width, and height, theoretical physics suggests there could be more hidden from our perception. Neutron stars, with their extreme gravitational fields and dense cores, offer a unique laboratory to test these ideas. The intense gravity of a neutron star could warp space-time in ways that reveal the presence of additional dimensions. For instance, if extra dimensions exist, the gravitational waves produced by neutron star collisions might carry subtle signatures that differ from predictions based on 3 dimensions alone. Scientists are also studying how the behavior of matter on a neutron star's surface might hint at these hidden dimensions. Theories propose that particles in such extreme environments could interact in ways that only make sense if extra dimensions are at play. By observing neutron stars, we're not just learning about these stellar remnants, we're probing the very fabric of reality itself. This connection between neutron stars and extra dimensions could reshape our understanding of the cosmos, taking us one step closer to solving one of physics' greatest puzzles. Now, let's turn our attention to how neutron stars might play a role in the formation of black holes. Shifting our focus to one of the most dramatic transformations in the cosmos, let's explore how neutron stars can become black holes. Neutron stars are already incredibly dense, packing the mass of a star into a sphere just a few miles across. But under certain conditions, even these extreme objects can't withstand their own gravity. When a neutron star gains too much mass, either by colliding with another neutron star or by pulling in matter from a nearby companion, its core can become so compressed that it reaches a critical threshold. This is known as the Tolman-Oppenheimer-Volkoff limit, the point at which the neutron star's internal pressure can no longer counteract the crushing force of gravity. Once this limit is crossed, the star collapses inward, forming a black hole. This process is not only a testament to the incredible power of gravity, but also a crucial link in the life cycle of stars. The collapse of a neutron star into a black hole can produce some of the most energetic events in the universe, including intense bursts of gamma rays and gravitational waves. Scientists study these events to better understand the conditions that lead to black hole formation and to test the limits of our physical theories. By observing neutron stars on the brink of collapse, we're gaining insights into the final stages of stellar evolution and the birth of some of the universe's most mysterious objects. Next, we'll delve into the intriguing idea that neutron stars might help us detect cosmic strings, hypothetical structures that could reshape our understanding of space-time. Now, let's venture into an even more speculative realm of cosmic mysteries: the search for cosmic strings. Neutron stars, with their extreme gravitational fields and precise signals, could play a key role in uncovering these elusive structures. Cosmic strings are hypothetical one-dimensional objects thought to have formed in the early universe, essentially rips or defects in the fabric of space-time. If they exist, these strings would be incredibly thin but unimaginably dense, stretching across vast distances and exerting a gravitational influence on their surroundings. So, how do neutron stars fit into this picture? Because neutron stars are so sensitive to gravitational effects, their behavior and the signals they emit could potentially reveal distortions caused by cosmic strings. For example, if a cosmic string were to pass near a neutron star, it might subtly alter the star's rotation or even cause a detectable glitch in its pulsar signal. Scientists are also exploring whether cosmic strings could leave imprints on gravitational waves produced by neutron star collisions. While cosmic strings remain unconfirmed, they could provide profound insights into the fundamental nature of the universe, including the unification of forces and the structure of space-time itself. By studying neutron stars, we're not only exploring the remnants of dead stars, but also peering into the very framework of reality, potentially uncovering clues to one of the universe's deepest secrets. Up next, we'll investigate how neutron stars might help us understand the enigmatic realm of quantum gravity. Turning our focus to the cutting edge of physics, neutron stars may hold the key to understanding one of science's greatest challenges: quantum gravity. For decades, scientists have sought to unify quantum mechanics, which governs the behavior of particles at the smallest scales, with gravity, which shapes the universe on the grandest scales. Neutron stars, with their extreme conditions, offer a unique laboratory to test theories that attempt to bridge this divide. These stars are so dense that their cores may contain exotic states of matter, pushing the limits of our understanding of physics. The intense gravitational fields near neutron stars also create environments where quantum effects and gravity interact in ways we can't replicate on Earth. For instance, researchers are studying how the behavior of particles in these extreme conditions might reveal clues about the elusive graviton, the hypothetical particle thought to mediate gravity. Additionally, the precise timing of pulsar signals from neutron stars could help detect subtle deviations from Einstein's theory of general relativity, pointing toward a quantum theory of gravity. By observing neutron stars, we're not just studying the remnants of stellar explosions, we're probing the very fabric of the universe, searching for the missing piece that could unite quantum mechanics and gravity. Next, we'll delve into the fascinating possibility of planets orbiting neutron stars and how they differ from planets around regular stars. Moving into the realm of cosmic oddities, let's explore the fascinating idea of planets orbiting neutron stars. While planets typically form around regular stars like our Sun, neutron stars present a completely different environment for planetary systems. Imagine a world where the parent star is not a glowing ball of gas but an ultra-dense remnant of a supernova. These planets, often referred to as pulsar planets, were first discovered in the early 1990s orbiting a neutron star known as PSRB 1257+12. What makes these planets so unique is the extreme conditions they endure. The intense radiation and strong magnetic fields from the neutron star create a hostile environment, making it unlikely for life as we know it to survive. Additionally, the gravitational dynamics are vastly different. A planet orbiting a neutron star would experience tidal forces far stronger than those around a regular star, potentially distorting its shape or even tearing it apart over time. Yet, despite these challenges, these planets offer valuable insights into the diversity of planetary systems. Studying pulsar planets helps astronomers understand how planets form and evolve in environments drastically different from our own. As we continue our exploration of neutron stars, we'll next dive into their role in shaping the evolution of the Milky Way. Shifting our gaze to the larger picture, let's uncover the profound influence neutron stars have had on the evolution of the Milky Way. These cosmic powerhouses, born from the explosive deaths of massive stars, have played a pivotal role in shaping our galaxy's structure and history. When a neutron star forms, the energy released during the supernova explosion triggers the collapse and compression of nearby gas clouds, often igniting the birth of new stars. This process, known as triggered star formation, contributes to the dynamic and ever-changing nature of the galaxy. Additionally, neutron stars, especially those in binary systems, can release bursts of energy and matter into their surroundings, enriching the interstellar medium with heavy elements like gold and platinum. These elements, forged in neutron star collisions, become the building blocks for future generations of stars and planets. Over billions of years, the gravitational interactions of neutron stars with other celestial bodies have also helped to sculpt the spiral arms and central bulge of the Milky Way. By studying these interactions, astronomers gain insights into the forces that have driven the galaxy's evolution over cosmic time. As we continue to probe the mysteries of neutron stars, we'll next explore their role in producing neutrinos, particles that hold clues to some of the universe's deepest secrets. Turning our attention to one of the universe's most enigmatic particles, let's delve into how neutron stars play a crucial role in the search for neutrinos. Neutrinos are incredibly tiny, nearly massless particles that rarely interact with matter, making them exceptionally difficult to detect. Despite their elusive nature, neutron stars are among the most powerful sources of these particles in the cosmos. When a neutron star forms during a supernova explosion, the intense energy released generates a flood of neutrinos which stream out into space at nearly the speed of light. In fact, more than 99% of the energy from a supernova is carried away by neutrinos, making them a key player in the explosive death of massive stars. Neutron stars in binary systems also produce neutrinos, especially during collisions or when matter from a companion star spirals onto the neutron star's surface, creating conditions of extreme heat and pressure. These neutrinos can travel vast distances through space, passing through entire planets and stars without being absorbed. Detecting neutrinos from neutron stars provides scientists with a unique window into the inner workings of these dense objects, revealing details about their composition, temperature, and energy processes. As we continue to improve our neutrino detection technologies, such as giant underground detectors, we unlock new ways to study neutron stars and the fundamental physics that govern our universe. With this understanding, we'll next explore how neutron stars might help us uncover the mysteries of dark energy, the force accelerating the expansion of the cosmos. Now, let's shift our gaze to another cosmic mystery: dark energy, the invisible force propelling the universe's expansion. Neutron stars might just hold the key to unlocking its secrets. Dark energy is one of the most puzzling phenomena in modern astrophysics, making up around 68% of the universe's energy content. But how do neutron stars fit into this? Their extreme gravitational fields and precise behavior make them natural laboratories for testing theories about the universe's expansion. By studying the gravitational waves emitted from neutron star collisions, scientists can measure how quickly the universe is stretching. These waves act as cosmic rulers, helping astronomers track changes in the distance between objects over time. Additionally, neutron stars in binary systems provide unique opportunities to observe the effects of dark energy. As these systems orbit one another, their movements create ripples in spacetime that can be analyzed to detect subtle influences from dark energy. Some theories even suggest that neutron stars might interact with dark energy in ways we don't yet fully understand, potentially revealing new facets of this enigmatic force. As our detection methods grow more sophisticated, from advanced gravitational wave observatories to space-based telescopes, neutron stars will continue to serve as invaluable tools in the quest to decipher dark energy's role in the cosmos. Next, we'll turn our attention to the intriguing possibility of time crystals and how neutron stars might be linked to this cutting-edge concept. Exploring the cutting-edge concept of time crystals, we find that neutron stars might hold fascinating clues. Time crystals are theoretical structures that exhibit periodic motion in time, even without an external energy source. Unlike ordinary crystals, which repeat their patterns in space, time crystals repeat their patterns over time, creating a never-ending cycle of movement. This idea, first proposed in 2012, challenges our understanding of physics and the nature of order in the universe. So, how do neutron stars fit into this? Their extreme environments, with crushing densities and intense magnetic fields, could potentially host conditions suitable for time crystal behavior. The rapid rotation of neutron stars, combined with their unique internal structures, might create systems where time symmetry is broken, a key feature of time crystals. Some scientists speculate that the strange, rhythmic signals emitted by certain neutron stars, like pulsars, could be linked to time crystal phenomena. Additionally, the precise measurements of neutron star behavior allowed by gravitational wave observatories could provide evidence for these exotic structures. If time crystals exist, they could revolutionize our understanding of quantum mechanics and the fundamental nature of time itself. As researchers continue to investigate these possibilities, neutron stars may serve as a cosmic testing ground for one of the most groundbreaking concepts in modern physics. Next, we'll look ahead to the future of neutron star research and the exciting discoveries that await us. Stepping into the future of neutron star research, we find a landscape brimming with potential and groundbreaking opportunities. The next generation of telescopes, such as the upcoming Square Kilometre Array, is set to revolutionize our ability to observe these cosmic objects in unprecedented detail. With its immense sensitivity, this telescope will allow us to detect faint signals from distant neutron stars, shedding light on their behavior and the extreme physics they embody. Additionally, space missions like the European Space Agency's Advanced Telescope for High-Energy Astrophysics, or Athena, will provide new insights into the high-energy phenomena associated with neutron stars, from their powerful magnetic fields to their explosive collisions. Advancements in gravitational wave detection technology are also paving the way for deeper exploration. Future observatories like the Laser Interferometer Space Antenna, or LISA, will be able to detect gravitational waves from neutron star mergers with greater precision, offering clues about their internal structure and the nature of matter under extreme conditions. Beyond hardware, computational models and artificial intelligence are transforming how we analyze data, enabling scientists to simulate neutron star environments and predict their behavior with remarkable accuracy. These tools will help unravel mysteries such as the equation of state governing neutron star matter, a key puzzle in modern astrophysics. As international collaborations expand, bringing together experts from diverse fields, we can expect discoveries that challenge our understanding of the universe. From probing the origins of heavy elements to testing theories of quantum gravity, neutron stars will remain at the forefront of cosmic exploration. The journey ahead promises not only to deepen our knowledge but also to inspire awe as we uncover the secrets of these extraordinary remnants of stellar evolution. From the birth of neutron stars in the fiery aftermath of supernova to their role as cosmic lighthouses pulsating across the universe, these extraordinary objects have left us in awe of their sheer power and mystery. We've explored how their unimaginable density defies comprehension. Their magnetic fields dwarf Earth's in strength, and their collisions create the very elements that make up our world. Neutron stars have not only shaped the cosmos but also deepened our understanding of physics, from testing the limits of relativity to offering glimpses into the nature of matter under extreme conditions. They've shown us how the universe operates on scales both vast and minute, from gravitational waves rippling through space-time to the rhythm of pulsar beams echoing across the void. These 50 facts have taken us on a journey through the life, death, and legacy of neutron stars, revealing how they connect to everything from the formation of galaxies to the origins of life itself. As we continue to study these cosmic marvels, they remind us of how much there is still to discover in the universe. If you've enjoyed this deep dive into the mysteries of neutron stars, don't forget to like this video, subscribe to the channel, and hit that notification bell so you never miss out on our next exploration of the cosmos. The universe is full of wonders, and we're just getting started.